Hoover High School AP Chemistry, we're now into our 6th unit, and this deals with the subject of kinetics. And this is definitely an AP level subject, so I want you to work hard this week to understand as much of it as you can, all of it if possible, and you will definitely see questions on the advanced placement exam dealing with this subject. So what is kinetics? Kinetics is the study of how fast a chemical reaction occurs. It's just that simple. It also deals somewhat with the mechanisms that determine whether a chemical reaction will take place or not. We'll deal with that later. Similarly, kinetics can be used to see how far from reactants to products a reaction has proceeded in a particular amount of time. So it has to do with the speed of a reaction in the simplest sense. The proper term for how fast something happens is called rate. Rate is the change in a variable per unit of time. Chemical kinetics is interested in two rates. One, the molar concentration, number of moles per unit time, how many moles increase or decrease in the reaction of each product or reactant, and two, the pressure per unit time. So it can also be used with gases in relation to their pressure, their gas pressures. So we'll review. Molarity is moles of solute per liters of solution. It's how much powdered lemonade mix you put into your water. And when you mix those two, it's called a solution. So it's how much of the lemonade mix you put in. You put in a lot, it's a higher molarity. You don't put in very much, it's a lower molarity. So molar concentration per unit takes molarity and puts it in the numerator over time. So it's how fast is the molarity of a reactant or a product in a chemical reaction changing. If it's a reactant, it's going to be decreasing. It's going to be used up as the reaction goes on. If it's a product on the right side of the equation, it's going to be produced. The concentration is going to go up per unit of time. So for example, how many moles per liter of a reactant are used up each minute, or how many moles per liter of a product are produced each second? The brackets are used to express molar concentrations. So the rate expression for a reactant A is written like this. It's negative delta concentration of A over time. So what it's saying is that you have a change, that's the delta, in the concentration of A in a certain amount of time. And the negative sign indicates that the concentration of the reactant is being reduced. The reactant is being used up. The rate expression for product B is written as delta concentration of B over change in time. This expression is positive because products are being produced. All right, something that you're going to see, not just in this unit, but in future units, and we will practice these as we go along, are particulate diagrams. So this image is called a particulate diagram. A particulate diagram uses symbols for reactants and products. The symbols are shown in proportion to the number of moles in the reaction. So if you look at the first one, the first row of circles, you'll notice that it has a certain number of reactants. Those would be the oval, blue ovals, and the red circles. And all you have is reactants at that point. As you go from left to right, and it ends up at 45 minutes over on the far right side, you end up with these elliptical purple ellipses. Those are the products. That's what's being produced. So you'll notice as you go along, you have fewer and fewer of the reactants and more of the product, the purple ellipses. At the end, you have nothing but products over at the end. If you look at the second reaction, D plus E goes to F, you start off with just reactants. Those are the yellow ovals and the blue circles. And as you go across, you end up at the end of 45 minutes with some of both. The products are going to be the green ellipses. Now, two possible things can happen. That second reaction takes longer to complete, and therefore it's not complete, so you still have some reactants in there. It might be that that reaction takes 2 hours to complete, and so you just haven't given it enough time at 45 minutes. There's another possibility is that reactant doesn't go all the way to completion. It stops in the middle. And a lot of reactions, I would even say most reactions, do that. We've always treated a reaction as though it goes from all reactants on the left and turns into all products on the right by the end of the reaction. That's not true all the time, and the subject we're going to deal with in the future, called equilibrium, deals with where that middle ground is, that balance is between the number of products and number of reactants. So in this case, the reaction might be over, and it might have a certain amount of products and still have a certain amount of the reactants, the blue circles and the yellow ovals, left over. That's not technically the case for a reason that you don't know, and that is, I'm going to tell you though, is that DE with the arrow to F implies it's a one-way reaction. It should go all the way to completion. It should not stop in the middle. So the best assumption we can make about DE to F is that it just hasn't had enough time to complete in 45 minutes. It will take it longer to go all the way so that you have nothing but the green ellipses in that last circle there. Okay, this is a typical graph of a reactant and a product and what happens over time. So this graph shows the concentration of reactants and products from the beginning of the reaction until time equals 30 seconds. At the beginning, everything is reactant. So if you look to the far left, you see it up at 0.4 is reactants. That's all you have. You don't have anything on the red line yet, which is products, what's going to be produced. So at the beginning, everything is reactant, black line, and there are no products, red line. As the reaction proceeds for 30 seconds, most of the reactants turn to products. You can see that they haven't all turned to products, and again, it may be that that reaction just stops right there and finds an equilibrium where you have some reactants and some products, or it could be it just hasn't had enough time. 30 seconds isn't enough time for it to complete the entire process of going from all reactants to all products. The steeper the line, the faster the concentration is changing. So for the black line, it's decreasing. It's a reactant. The reactants are being consumed. They're being used up. And that happens the fastest at the beginning of the reaction. For the products, since the reactants are being used up and turned to products faster, it will also increase the products faster. So you notice that both of the lines are steepest near the beginning. The reactant is a negative slope and the products is a positive slope, but they're both at their steepest at the beginning of the reaction. Once the reactants start getting used up, then the reaction goes slower and slower. It still continues, but it goes slower and slower. Here's an analogy I like to use. Imagine I took everyone in this class and put them in an empty classroom and took all the chairs out, and so it was just, the floor was just wide open. And I blindfolded you. And now I have you walk around, and when you bump into somebody, that symbolizes a chemical reaction. So you and that other person will leave the room. Well, at the beginning with 30 students, everybody's going to be bumping into each other pretty quickly. People are going to be finding each other, bumping into each other quickly. So quickly the reaction will take place quickly because there's a high concentration of people. But as people start to leave the room after they've reacted with someone else, there's fewer people left in the room. Maybe at some point there's only 4 people left. They're not going to hit each other very often because there's so much space between them. And so the reaction will move much slower. It's the same thing here. When you have a high concentration of particles, molecules, or atoms, they're going to hit each other a lot more frequently. As they start to be reacted though and turn into products, and you have fewer and fewer of the reactants, they're not going to find each other quite as quickly, and the reaction is going to move slower towards the end. So the reactants line is steepest at the beginning when the concentration is greatest. The negative slope means that the concentration of reactants is decreasing. The product line is increasing rapidly at the beginning when the reaction is fastest. So they're both increasing or decreasing fastest at the beginning. Okay, the rate or speed is greatest where the slope is steepest, and the rate speed is lowest where the slope is the least steep. By the way, this is a graph of concentration on the vertical axis, molar concentration, in other words, how many moles per liter you have, versus time on the bottom on the horizontal axis. Now you can also have a graph similarly with pressure. And so kinetics also applies to gases. Instead of molar concentrations, gas pressures are placed on the vertical axis. So let's take an example of a rate expression. A rate expression equates the rate at which the reactants are being used up and the products are being produced. So here's a simple little example. Faith and Hector are making a booklet for the Mesa Club. The booklet has 5 pages and requires 3 staples. So the process can be written in the form of a chemical equation. 5 paper plus 3 staple will result in 1 booklet. If it takes Faith and Hector 1 minute to create 1 booklet, then we can write the process as the rate with time included. So let's say it takes 1 minute. So that means each of those things is going to happen in 1 minute. 5 pieces of paper is going to be consumed, and so it's a -5 because it's being used up. 3 staples are going to be consumed. It's a -3 because they're being used up. And it's going to produce over on the right-hand side 1 booklet. That's positive because that's being produced. So the reactants on the left are consumed, so there's a negative sign in front to indicate that their concentration is decreasing. The product, the booklets, are increasing in number, in concentration. We see that in 1 minute we consume 5 pieces of paper, 3 staples to produce 1 booklet. A rate expression seeks to set these 3 rates equal to one another. The rate expression also adjusts the negative sign since rates must be positive values. Remember that. A rate has to be a positive number. It can never be a negative number. So let's start with the paper. We see that the paper is consumed 5 times as fast as booklets are produced. So in 1 minute, you're going to use up 5 pieces of paper, and you're going to produce 1 booklet. So the paper is being used up at 5 times. Each piece of paper is being used up as 5 times the rate as a booklet is being produced. So if we multiply the paper by the term -1/5, then the 2 rates will be equal. In other words, -1/5 times -5 will give you 1. So you'll have 1 paper per minute. So that's how you set the rate of the paper equal to the rate of the booklet. Also, if we multiply the staple term by -1/3, then the rate of staples being consumed will equal the rate of booklets being produced. And you can do the same thing with booklets, making it 1/1 positive because it's being produced. You don't really need to do that. But if you want to just go ahead and complete the idea there. So rates must be positive. So we write the coefficients on the reactant side with negative signs. So let's take a very simple reaction. You could think of this as 2 hydrogen atoms or 2 moles of hydrogen atoms being put together to create 1 mole of hydrogen molecules. That would be a simple example of what this relationship could be. So assume this reaction takes 1 minute to complete. In 1 minute, 2 moles per liter of substance A are used, and 1 mole of A2 is being produced. The rates for each of these could be written as follows. Negative delta of 2A per minute because it's decreasing, and you have a change of 2 moles, and positive delta of A2 in 1 minute. So those 2 things would have to happen in the same amount of time. You'd have to use up the 2 moles of A in 1 minute to create the 1 mole of A2. So this is a rate expression for that equation. You want to set the rates equal to each other. So since the left side, the reactant side, is happening twice as fast as the product side, you're using up 2 moles of A for every 1 mole of A2 you're producing. If you want to equate those 2 rates, you multiply the reactant side by -1/2. So -1/2 times -2 would give you +1, and that would equal to +1 on the right-hand side. These expressions equate the rates, how fast, at which these 2 processes take place. The negative sign in front of negative delta 2A indicates that the molar concentration of A is decreasing. It is not normally written. It is implied because it's a reactant. In other words, since you know you're on the reactant side, you don't have to write the negative sign. You know since it's a reactant, it's going to be decreasing. So the negative sign is implied that it's there, even though you don't actually write it. The minus sign in front of the expression -1/2 indicates that a rate number must be positive. So the double negative signs, again, the one inside the brackets there is not normally written, but it's implied. So the double negative sign makes this rate positive. Rates always have to be positive. So there's the reaction, and there's the rate expression for that reaction. To relate how much of a product is made when a certain amount of reactant is consumed, the two expressions are equated. Since twice as many moles of A is being used as A2 is being produced, the -1/2 term must be placed in front of the reactant side to equate the two sides. Normally, the decreasing reactant 2A does not show the negative sign inside the brackets since it is a reactant and is known to be decreasing. Okay, so here's a reaction that has two reactants on the left and two products on the right. Capital A, B, C, D just represent different elements or compounds that could be in the reaction, and the small a, B, C, D represent the coefficients that would be in front of those in a typical chemical reaction, as you've seen many times. So generally, to write a rate expression for any reaction, the reciprocal, that is flip, the coefficient is placed in front of the molar rate of change for each reactant product. All of the reactants and products can then be equated. So all of the reactants and products can then be equated here. So if you look at that, take a look at that down there. That's what we just talked about in the last couple of slides. So convince yourself that that's how you would equate all of the rates. You have the change for reactants, that's A and B. Those are negative numbers. So their coefficients are going to be, you flip the reciprocal, you take the reciprocal of the coefficient. So for A, it's 1/A. And since it's a reactant, you have to make it negative because the delta A over T is decreasing. That's negative. So the negative becomes a positive. Remember, we don't write the negative sign normally inside of delta A. It's implied because it's a reactant. So that is a double negative, even though you only see one negative sign there. For B, it's the same thing. Okay, delta B over T is negative, so the negative out in front of -1/B is going to make that a positive, and the 1/B is the reciprocal. And same for C and D, those are products, therefore they're positive, so you don't put a negative sign in front, and that's how you would write it for a full chemical equation. So let's take this chemical equation. Why don't you test yourself before you want, pause the video and see if you can write the rate expression for all 5 of these, the 3 reactants and the 2 products. See if you can do that, and you can pause, and now I'm going to go ahead and show you. So write the complete rate expression for the reaction. Answer: to take the reciprocal of each coefficient and place a minus sign in front if it is a reactant. The rate expression for the entire reaction is, so see if that's what you got. You just take the reciprocal of the coefficients. If they're on the reactant side, you put a negative sign. They're all equal to each other, so it's just a bunch of equal signs in between each of those different parts of the equation. And that's how you would do that. Okay. The minus sign above BRO minus and BR minus simply means they're ions, they're anions. That has nothing to do with what we're talking about here. Okay, so BrO3 minus. There it is, 1/1, negative because it's reactant. 5Br minus becomes -1/5, delta Br minus over T. The hydrogen, it becomes -1/6. It's a reactant, so it's a negative sign, delta H over T. Now we go over to the product side. 3Br2 becomes 1/3. It's positive because it's being produced. It's increasing in value. And 3H2O. And there it is, it's 1/3 H2O. Alright, so let's actually do a problem and see where this is used. This helps us to understand how the rate of one of the products or reactants will change given a certain amount of change of one of the other products or reactants. So assume that the value of delta BrO3 over delta T equals -1/5 times 10 to the -2 molar per second. Again, that's what rate is expressed in. It's molarity. How much is the molarity changing each second? Determine the rate of formation of H2O. So you go back to the equation on the previous slide, and you'd only need to deal with BrO3 and H2O. You don't need to have everything else. So you can see that those two are equal to each other. Now it gives us an actual number for this, for delta BrO3 over T. And that number is -1.5 times 10 to the -2 molar per second. So you come down here and you substitute that number in for what's in that red box there. And you end up with, remember that delta BrO3 minus over T is a negative number. So the -1/1 in front of it is going to make it into a positive number. Again, you got to get used to that concept that there's no negative sign inside of delta BrO3 over T. Again, that negative sign you see up there is anion, has nothing to do with what we're talking about. So it makes the 1.5 times 10 to the -2 a positive number. Then over on the right you have 1/3 H2O. So now it just becomes an algebra problem. You multiply both sides by 3, and then the 3's on the right hand side, the 3 and the 1/3 cancel. So you end up with 3 times 1.5 times 10 to the -2, and that's going to equal 4.5 times 10 to the -2. So what you see is, if you look at the equation, we'll go back to the original chemical equation. You're producing 3 moles of H2O for every 1 mole of BrO3 that you're using up. And so if you used up 1.5 times 10 to the -2 moles per second, molar per second, then you're going to have 3 times that much water being produced, 4.5 times 10 to the -2, and the unit there is not written. It should be also be molar per second. Okay, now the rate law. This is really the more important equation dealing with kinetics. And we're going to get into how a rate law works. So take the following reaction. We've done that. We've looked at that, and the rate law has the following form. The rate of the reaction at a specific moment in time, and I'm going to keep emphasizing that point, it's at a very specific moment in time, is equal to something called the rate constant, K, and times the molar concentration of A. Let me go ahead and put these all up. The rate constant K, that's the third one down. Let's talk about that. That's a function of temperature. Generally speaking, the hotter the reaction is, the more heat is in it, the faster the reaction will take place. Why? Very simply because the molecules are moving faster, they're smashing into each other harder, and the reaction is going to happen faster. So that's what the K represents. It's kind of a way of working temperature into this reaction, into this equation rather. A is the concentration of reactant A. B is the molar concentration of reactant B. You could have C and D. You could have more than 2 reactants, but we're keeping it at 2 for right now for this equation. And finally, the exponents X and Y. Those are determined experimentally. They are not the coefficients A and B. One thing you notice about this reaction is it's a function only of the reactants A and B. The products C and D have nothing to do with how fast the reaction takes place. Only the reactants A and B have something to do with that. So the order of a reactant is the exponent X or Y on the reactant. So let's learn about that. It's almost kind of like order in a polynomial when you're doing math, when you're in math class, but not exactly the same. So a to the first has an exponent of 1, and that's usually not written obviously when you have an exponent of 1. So that's read the reaction is first order in A. That's how you would read that. If B squared has an exponent of 2. I'm just making up some examples here. This is read the reaction is second order in B. The order of the overall reaction is the sum of the orders of the reactants. So the reaction, the rate equals K, A raised to the first power, B to the second. So you add the exponents. 2 plus 1 equals 3. So the rate is a third order reaction. And that gets significant later on as we talk a little bit more about this. So variables in a rate law. So let's take the rate law and give the relationship between rate Okay, so the rate law gives the relationship between the rate speed of the reaction and the concentration of A in molarity, the concentration of B, also in molarity, and the rate constant, which is a function of temperature. Generally, the higher temperature produces a faster rate of reaction. Okay, so this is a summary of how different order reactants affect reactions. If it's a zero order, and it can be, you can have a zero order. If the reaction is zero order, then the concentration does not affect the rate of the reaction. In other words, you can increase the concentration of the reactants or lower it all you want. The reaction will take place at the same speed. If it's first order, and most reactions are first order reactions. If the reaction is first order, then doubling the concentration doubles the rate of reaction. It kind of makes sense. You know, if you have twice as many molecules in there smashing into each other, then the reaction is going to happen twice as fast. So that kind of makes some logical sense, and that's a first order reaction. And as I say, most reactions in chemistry and in nature are first order reactions. A2, A squared. If the reaction is second order, then doubling the concentration quadruples the rate of the reaction. The increase in rate is the increase in concentration squared. So you're squaring the concentration to get the rate, how fast the reaction is taking place. So example, how is the rate of the following reaction affected by changes in the concentrations of A and B? So there's the equation we're going to use. So we're going to say that A is a second order reactant and B is a first order reactant. So what you do is just invent some numbers for each variable. The exponents are fixed. You can't change that 2 or that 1 for the exponents. Don't worry about units of measure. Okay, so make all variables equal to 1, and you plug them into A and B and into K as well. K is really not a variable. The rate constant is fixed for a certain reaction at a certain temperature. But if you do that, you'll end up with 1. If you double the concentration of A, that is, you put a 2 in for A instead of a 1, then you end up with the rate going up not 2 times as much, but 4 times faster. The rate will be 4 times faster if you double the concentration of a second order reactant. And finally, if you double the concentration of B, which is a first order reactant, it will double the concentration. So this next page will kind of summarize that again. So conclusions for this example: make all variables equal to 1. The initial reaction, that's the initial reaction. So your rate is simply 1. If you double the concentration of a second order A, then the rate will quadruple. It'll be 4 times faster. Doubling the concentration of a second order reactant quadruples 4 times the rate speed of the reaction. And 3, double the concentration of first order B. Then if you double that, then the reaction will go twice as fast. So doubling the concentration of a first order reactant doubles 2 times the rate speed of the reaction. Okay, so that gives you a good little introduction to kinetics and what kinetics is, what it's all about. On the next video, we're going to take up how to actually calculate a rate law based on experimental data. And that's an important concept that you could be asked about on the AP exam. All right, so we'll see you on the next video.